Okay, so we start here. Hello, welcome to the webinar on the glaciers and groundwater interactions, challenges in a changing climate, organized by the International Association of Hydrogeologists and sponsored by UN Water and UNESCO. My name is Masaki Hayashi from the University of Calgary in Canada. I am your master of ceremonies for this webinar. We will start the webinar with a pre-recorded video message by Koen Verbist, representing UNESCO Intergovernmental Hydrological Program. Please, Olivia.
Yep, let me just get that.
Ladies and gentlemen, on behalf of the UNESCO Intergovernmental Hydrological Program, it's a pleasure to address you here on the occasion of the first ever World Day for Glaciers. While we celebrate the day, we all know that glacier loss is a serious threat to natural and human water supplies. In many parts of the world, we also know that melting of glaciers and ice sheets are the biggest cause of sea level rise in recent decades, as highlighted by the IPCC in 2022. So why is this topic so important for UNESCO? 70% of all fresh water is stored in the cryosphere. 10% of all glaciers are located in only 50 UNESCO World Heritage Sites. At the same time, a recent study by UNESCO highlighted that already half of all of those glaciers in World Heritage Sites are expected to disappear by 2100. Harming ecosystems, disrupting water supplies for many, and destroy important records of Earth's climate history. For indigenous peoples and local communities, they can be sacred places woven into centuries-old traditions and knowledge systems. UNESCO HP, in collaboration with key partners like the IAH, therefore play a key role as a platform for scientific cooperation and networking, contributing to assessing and monitoring changes in snow, glaciers, and water resources, as well as identifying pathways for adaptation. UNESCO is therefore co-coordinating with the World Meteorological Organization the implementation of the UN General Assembly resolution that declared 2025 as the International Year of Glacier Preservation. The resolution also refers to UNESCO's historical work, of which maybe some of you contributed, which called for a worldwide inventory of existing perennial ice and snow masses during the international hydrological decades in the periods 1965 to 1974. UNESCO has also been supporting glaciologists and hydrologists from all over the world, providing them with a platform to undertake research studies on cryospheric changes and their impact on water resources and groundwater changes for more than half a century. One example, for example, is the work in the Andes that resulted in the publication of the Andean Glacier and Water Atlas, to document the impact of glacier retreat on water resources. In 2021, UNESCO launched a new Central Asia Regional Scientific Program with funding support from the Adaptation Fund and the Global Environmental Facility to map out the region's glaciers and develop cryosphere management plans. The project will also map the most vulnerable areas to deploy early warning systems for populations most at risk from glacier lake outburst floods. As a contribution to the International Year of Glacier Preservation 2025, you have seen that various events already have taken place, including, for example, preparatory events at the UNFCCC, the COPs, and the launch of the year in January. So upcoming events include also the International Conference in Dushanbe, planned for May 2025, to which you are all invited. Yesterday, we also concluded the first brainstorming session to shape the new decade of action for cryospheric sciences that will run from 2025 until 2034, and which will be coordinated by UNESCO. We expect to launch the decade during the UN Ocean Conference in Nice on 8th of June of this year. The decade will certainly provide a longer period to achieve key milestones for our cryosphere and to address some of the key scientific challenges. This session therefore comes at a very opportune time to identify new opportunities for collaboration to address the impacts of climate change on our frozen water resources. And I would therefore also like to wish you a fruitful discussion and hopefully also input for our further discussions for the year and for the decade. We look forward to continuing our collaboration with IAH and to achieve these ambitious goals. Thank you so much.
Well, thank you. Next, we have a live message from Felicia Baccarello, representing UN Water.
Thank you very much. And I hope colleagues can hear me well.
Yep, we can hear you.
Wonderful. First and foremost, good morning, good afternoon, and good evening, everybody. And as my colleague Cohen said, happy first World Day of Glaciers. It's wonderful to be here with you today on behalf of UN Water. And if you would allow me, I will just share a couple of slides, not very many. And if you can see my screen, first and foremost, I would just like to say, again, thank you to the International Association of Hydrogeologists and thank you to UNESCO IHP for organizing the webinar and for your continued leadership in the field of groundwater and glacier interactions. This event is an excellent example of how UN Water members and partners work together, combining our expertise to address complex water challenges. And it's been wonderful to see that so many events have been organized yesterday, today, and so many other events are being organized tomorrow, all of them reinforcing how important glacier preservation is through World Water Day, through the International Day of Glaciers, and of course, through the entire year. These type of collaborations are essential for us to fill knowledge gaps, to share policy, and to really drive global action on water security. Now, glaciers and groundwater are deeply connected, and the majority of you probably know this even better than I do. As glaciers melt in unprecedented rates, they impact not just the surface water flows, but also groundwater recharge, affecting long-term water availability. While a lot of research has been done on glacier retreat and its impact on rivers and lakes, the groundwater interactions remain underexplored, making discussions like today truly essential. To raise awareness and also to inspire action, the 2025 World Water Day campaign, which is coordinated by UNESCO and WMO, like Cohen said, on behalf of all of the UN Water family, really highlights how glacier preservation is a survival strategy for both people and the planet. As you can see, and as you probably know, every year the campaign reaches billions of people around the world. And this year is special because the campaign is aligned with joint celebration with the first UN Water Day of Glaciers. Now, what we have here on screen are really our three core messages for World Water Day. But what's important to remember here is that our frozen world is shrinking, which is making the water cycle more unpredictable and extreme. As a result of that, billions of people are being impacted by droughts, by floods, by landslides, and sea level rise. However, all of these challenges also have solutions. And what we're trying to focus on is really how can we make sure that we cut greenhouse gas emissions and how do we manage meltwater most sustainably for everybody in the world. If we are to save our glaciers, which is also the campaign slogan for this year, the science must be at the heart of solutions and glacier preservation must be central to our action plans on water and climate change. To achieve Sustainable Development Goal 6, which is ensuring availability and sustainable management of water and sanitation, we must invest in research that enhances our knowledge on groundwater glacier interactions and that helps communities adapt to changing water availability. We have a number of campaign assets that we have created the same way we do every single year to make sure that we raise as much awareness as possible and that we also lead to advocacy and outreach. Of course, collaboration is key. So by sharing expertise, data, and solutions, we can improve water security for future generations. And the UN Water Campaign provides resources that help, like I said, to drive awareness and drive action. Today's event and the collaboration that we're seeing all across the world is really a testament for the power of working together to advance scientific knowledge and to inform global action. Looking ahead, we also know that UNESCO will play a leading role in glacier preservation efforts, and Cohen already spoke about that in his video message. From me and from all of us at UN Water, we want to say thank you again. We want to encourage you to help us raise awareness and to help us really talk about glacier preservation this year. And I am very much looking forward to hearing from all of the speakers today and deep diving into all of these challenges and solutions a little bit better. Thank you very much. And I will be here also for any questions for the remaining of the event.
Thank you, Felicia. Now we move to the case study presentation. So first, I will show a few slides to set the stage for the case study presentations. So this picture it shows our long-term hydrological monitoring sites in Canada. So we have been studying this site for about 20 years. So it's a typical alpine watershed with the glacier hanging here. And then this is called a proglacial moraine. So there's no surface water we see, but then there is a large alpine stream coming out of this moraine. So we have monitored this system for about 20 years, and then it clearly shows that even in the middle of the summer, when there's not much snow left, only about 2% of water coming out of this river is sustained by glacial melt. So majority of water coming out of this proglacial stream is not coming directly from the glacial melt. And the reason is there is a lot of water stored inside this moraine. There are a lot of groundwater processes happening between the melting glacier and the stream outlet. So when we started this work about 20 years ago, indeed there was a little knowledge on this kind of system, but over the last 2 decades, many people have studied groundwater in the systems like this. And now we have a large body of literature on groundwater processes in proglacial environment. Example, this is a recent review paper on rock glaciers. So this picture shows a ice glacier and a debris-covered glacier, rock glacier, and the aquifer below, connecting this glacier to a stream. So the important thing is with the climate warming, so the boundary between rock glacier and debris-covered glacier is moving up, so as the boundary between debris-covered glacier and the glacier. So the glacier is indeed shrinking, but this proglacial aquifer is increasing. So World Water Day, we're going to be talking a lot about glacier, but it's also important to talk about groundwater processes. So we have case studies presentations by some people who are studying this system. And also we have panelists who has intimate knowledge of groundwater processes. Our first case study is presented by Sophie Violet from ENS, PSL, Université Paris, and Sorbonne University. I will just stop sharing. So please, Sophie, take it away.
Yeah, thank you, Masaki. I hope you can hear me. Okay, and blank screen. Okay, thank you for the invitation to give this talk as a representative of the International Association of the Hydrogeologists. My talk is about the impact of melting glaciers on groundwater. It is based on a literature review and some pieces of work performed in the frame of the Ice Hike project. This project is in partnership with Icelandic and French researchers and local stakeholders. Our literature review is based on temperate glaciers, meaning glaciers with a bottom at the melting point. Our literature review highlighted that the catchment areas of temperate glaciers are seriously affected by climate change. These catchments are the subject of in-depth studies from the point of view of glaciology and surface hydrology. Groundwater in these same catchments is much less frequently mentioned and even studied. The few available studies in the scientific literature on the groundwater compartment tend to show a particularly high recharge of aquifers by glacial meltwater depends on glacier geometry, mass balance state, and hydrogeological parameters, but varies between 25 to 50% depending on the system studied. The few available studies in the scientific literature tend to show a strong connection between surface water and groundwater, a fairly high hydraulic conductivity in moraine and till aquifers, and bedrock is often considered as non-aquifer. These characteristics suggest that groundwater from the catchment areas of temperate glaciers in the coastal zone could feed the French groundwater reserves offshore, as observed by Post in his co-author Around the World. In this paper, it is highlighted that some of these groundwater reserves offshore were constituted during the last glacial maximum. The hydrodynamical role of potentially deeper fracture aquifers remain unknown, and some questions have been raised. What are the potential effects on groundwater hydrodynamics, the corresponding water resources, and their availability to local population? How can groundwater mitigate or amplify meltwater released hazards such as flood, landslides, and seismic activities? What is the effect of fluvioglacial hydrosediment transport and erosion over the morphology of the proglacial zone? The following question can resume the main scientific challenges. What are the aquifers' responses to climate change that prevent us from predicting changes in water resources and the associated risks such as landslides, floods, droughts, and economic and human issues? This question can be declined depending on the targeted area. In the subglacial area, where and when do the water exchanges between the subglacial system and the aquifers occur? At which elevation under the glacier? And at which time of the year? This impacts the water pressure under the glacier, hence its basal sliding, and can lead to speed-up events. In the proglacial lake, how much groundwater contributes to and exfiltrates from the lake? It is important to assess their future evolution and prevent lake overflow. In the proglacial area, at what distance from the terminus does the groundwater starts to exfiltrate in stream, and what proportion is discharged on the surface? This is important for flood risk. The Ice Hike project aims to address some issues with these questions. How much glacial meltwater feeds the subglacial aquifers? What is the role of the aquifers in the spatio-temporal circulation of water through glacial catchment areas? In particular, what is their role in the dynamics of water flows contributing to the surface flow of rivers and the flow of water exported to the ocean? What impact will the loss of glacier mass due to global warming have on the hydrodynamic regime of aquifers? To this end, an observatory has been set up. The observations will feed the coupled glacial and groundwater flow numerical modeling, and the results will be shared with local stakeholders to provide guidelines and action. The observatory is set up southeast of Vatnajökull ice cap in Iceland. The 4 studied glaciers are fully temperate with proglacial lakes. The geothermal activity is weak, and there are 2 aquifers, the teal unconfined aquifer, represented in light brown on the map, and the basalt aquifer, represented in purple, partly unconfined and partly confined while covered by the teal. The climate was recorded at the open stations, which moved from one place to another from 1996 to 2022, but stayed at very low elevation. The climate is a maritime subpolar one, strongly moderated by the Gulf Stream influence. During winter, snow is abundant above 400 meters of elevation. The graphic on the left represents the annual total precipitation and average temperature for this period. Total annual rainfall increased from 1,200 millimeters to 1,630 millimeters, thus an increase of plus 36%, while the average annual temperature increased from 3.9 Celsius degree to 5.4 Celsius degree, thus an increase of plus 1.5 Celsius degree. These are the consequences of global warming and climate change. The upper right graphic shows the monthly average precipitation, while the lower right graph shows the monthly temperature. All months receive significant precipitation, and the lower values occur between May and August. The mean monthly temperatures are distributed over quite a narrow range, less than 12 Celsius degrees, and nearly always stay positive at low elevations, which is typical of subpolar maritime climate. Depending on the year, the glacial melt season is from May to September. Estimates of glacier meltwater were used to deduce the amount of water available for subglacial runoff and groundwater recharge in the subglacial zone, shown in light blue on the left graph. Subglacial meltwater averages 4,000 millimeters a year from 2010 to 2016 and varies seasonally, peaking in July and August. As shown on the right graph, the contribution of subglacial meltwater decreases as the glacier elevation rises. In the proglacial zone, the effective rainfall deduced from tons weight water balance, shown in dark blue on the left graph, is 1,000 millimeters a year on average from 1990 to 2010, and varies seasonally, shown, and the months with no effective rainfall are between April and August. Thus, the contribution of the glacial meltwater is 4 times higher than the effective rainfall. Since summer 2021, we have been recording groundwater levels and temperatures in several boreholes that tap either the teal or the basalt aquifer. We also record surface flows in rivers and water level in several lakes. In the proglacial area and along groundwater flow line going from the Flaherty Glacier to the coast, 4 new bore wells have been drilled in the Teal aquifer. The groundwater level records from September 2021 to September 2022. This graph shows upstream the groundwater level has a smoother response to rainfall, snow melt, and glacial meltwater. The groundwater level amplitude decreased from up to downstream, and this amplitude is around 2 meters for the area closest to the glacier and less than half a meter for the area furthest away. Downstream, the groundwater level is closer to the surface and the proglacial area is swampy. Recharge by snowmelt is visible in May and occurs a few days after the snow event. Recharge by glacial meltwater is visible in the Flow-3 borewell as shown in the second graph, with a significant increase in the water level in August and September. Depending on the location, the basalt aquifer can be unconfined while it is outcropping, or confined while it is covered by till and fluvio-glacial deposit, and it even can be artesian at some locations. This graph represents the time evolution of the water level recorded in the basalt aquifer from September 2021 to September 2022. In the proglacial area, the confined part of the basalt aquifer, the label are shown in bold, HA16, ISK 103, ISK 104, show groundwater level variation with much smaller amplitude and less than half a meter than in the unconfined parts, which are where the water level is over 1 meter in the other boreholes. Here, the monitoring of the water levels and the temperature allows us to identify that the till temperature, shown in red, follows the air temperature trend, shown in yellow, except at some periods when the till temperature is constant and the till water level, shown in blue, is low. This means that a flow of warmer water is coming from the warmer basalt aquifer below, showing a vertical upward leakage of basalt groundwater. During the melting season, we perform...
Aurelia, Theodora.
Sorry, I hear someone. During the melting season, we perform dye tracing experiments to characterize the subglacial channels, the rate of subglacial water infiltrating the aquifers, and the water flow velocities in the subglacial and proglacial area, respectively. Since 2023, 2 time-lapse cameras have been set up in the 2 hydrological sections to obtain continuous river flow rates. The river flow was monitored during the 2024 melting season with seismometers on 7 hydrological sections also. Validation of the water flow rate is obtained thanks to punctual dye and salt tracing, and the data treatment is in progress. Based on this data collection, we propose a glacio-hydrogeological conceptual model of the system, showing the water's pathway from the glacier surface to the aquifers and the surface flow. We estimate the contribution of the subglacial flow and the effective rainfall to the aquifer recharge and the runoff. The new data collection will improve this conceptual model. In conclusion, we can say aquifers are a key compartment of the water cycle in catchment held by temperate glaciers. Glacial meltwater is a significant contributor to aquifers. The remainder is surface runoff. Recharge of aquifers by glacier melt is higher in the subglacial zone than recharge by precipitation in the proglacial zone, and vertical upward leakage from the deep basalt aquifer to the shallow till aquifer may occur from time to time. As a perspective, we can highlight long-time monitoring of the water level and temperature in aquifers is required for a better characterization of their role in the water cycle, and coupled numerical modeling of glacial and groundwater flows will help us to understand and quantify the impact of glacial meltwater on aquifer dynamics. Thank you for your attention. And if you have any question, I'll try to answer them.
Thank you, Sophie. It's a really fascinating presentation. A lot of work going into monitoring these processes. So, Olivia, do you have any questions posed by the audience?
We haven't had any questions in yet. Just a reminder to everyone that you can enter some questions in the Q&A box at the bottom of the screen. We've got a question from one of our panelists, John, so let's go over to him.
Thanks, Sophie. Yeah, you mentioned at the start the kind of the plan to develop some models off of the back of all of this observation work that you've been doing. I just wanted to know how much progress have you made with that, and what are there specific kind of research questions that you're trying to answer by applying those models?
Thank you for the question, John. The model that we plan to use is Helmer-Hayes, with a version where there are the coupling in between the glacial flow and the groundwater, and the main question we have when we start this project was to understand what is the real relationship in between the glacier and the subglacial area. Does the water is flowing on the subsurface? Does it penetrate inside the ground, filling the tills? And are there any chance that some of the water goes through the bedrock? Because as often mentioned in the literature, bedrock is often viewed as an aquifer, a non-aquifer. But in our context of basalt, where the basalt can be fractured, and it's very interesting to check if the basalt is able to receive part of the water coming from the melting of the glacier. And our first data show that this might be possible. And so I think it's interesting to understand this relationship and this kind of exchange below the glacier.
Yeah, I agree. Thanks. Sounds really interesting. Thank you.
So Olivia, there are a couple of questions. Do you want to read them out?
Yeah, sure. We've got one from Ravi Apana here. It says, are you planning to share the slide deck afterwards? I'm sure we can do that for sure. Sophie, if you'd be happy to send over your slides. Felipe Fuentes says, I have a question. If there is a measurement of parameters like temperature, CE, and I'm not sure what that is.
Yeah, there are a few more. I can see them, so I can answer.
Yeah, sure. Okay.
At the moment, for the question of Felipe, which asked if I did some other measurements than temperature and water level measurement. At the moment, according to the financial support that we have, we are focusing mainly on the quantitative part of the comprehension of the quantitative part of the system, and we are not able to do chemistry and isotope, but that will be very great to be able to include this part of research in our work. That's a good question. Thank you. Alors, I want another question about Alan Edmonds. I was wondering if the plot of the till hydrograph and temperature came from the single borehole located in the proglacial area. Yes, they are coming from the same. In fact, the probe is able to measure the water pressure and the temperature together. So this is at the same location.
So I don't see any questions in the Q&A, but we still got time for a couple more questions. If there's none from the audience, I have one. Olivia, can I go ahead and ask a question?
Yeah, absolutely. Go for it.
Yeah, so it's interesting that precipitation is increasing with the temperature. So do you have a sense of the long-term trend of flow in this stream and also temperature of water in this stream?
That's a good question. Unfortunately, in our area, we only have one river with the record of the water discharge, and as the river is not, as the water discharge is not checked regularly, the confidence we can have on this measurement is not really high. So we do not have really a high record of the water discharge. And we do not have the measurement of the temperature in the stream, but that might be an interesting measurement to do. The difficulties in this area is to fix a system to make the measurement that can be not destroyed during the floods, because at some times the flooding events are very strong with transport of sediment, and all the material is destroyed, even some bridge and so on. So it's very difficult to find a kind of measurement that can be settled for a long time. That's a problem in this area.
Yeah, it's a hard work.
Yeah, it's why we are here.
So I see another question from Felipe. Do you have boreholes that have reached the bedrock?
The bedrock is basalt, and we have the chance in this area to have some borehole who reach the bedrock, the basalt, and I show some water level measurement in different places, because it was a campaign for a prospection of geothermal activity in the area, and it was unsucceed. But fortunately, we get access to this borehole. So we have almost 10 to 11 bore well who go to the bedrocks. Some of them are on the aquifer part of the basalt, because the water level is moving and so on. And when we did the measurement of the hydraulic conductivity, it's quite good. And some of others are only on the, the core of the basalt. So the water level is not really moving, and the hydraulic conductivity is very bad. So in fact, in this kind of aquifer, the hydraulic conductivity, so the hydrodynamic parameters are very heterogeneous from one location to another. So we plan also to improve the knowledge about the fracturation of the bedrock, for example, by geophysics, to have a better idea about the main pathway of the groundwater in this kind of fracture system.
Okay, well, thank you. So Felipe has one more question. Quick answer for this question. So is there a flow measured on the bedrock fractures? And also, is there any measurement of flow from springs coming out of the bedrock?
We do not measure yet the flow in the fracture. No, we do not. And it might be quite difficult, because this will need to have two boreholes, and to do, for example, dye tracing in between two boreholes if they are not too far from each other, and we are sure they are in connection. Unfortunately, we do not have this kind of setting. And the second part of the question.
Was there any measurement of flow from springs coming out of the bedrock?
Yeah, we have some spring, and there are some spring on the place, and we are measuring. But the measurement of the water flow from the spring is very punctual, so it gives less information than the record of the water level in the groundwater.
Okay, well, thank you, Sophie, and all the people who asked the questions. Yeah, the great presentation and questions. So the second case study is presented by Jonathan Mackay from the British Geological Survey. Jonathan, please go ahead.
Great, thanks everyone. I'll just share my screen. Great. Can you all see that?
Yes,
Yeah.
all good.
Brilliant, brilliant.
Yes.
Great. Well, thanks everyone for having me here today. I'm very glad to be here. So yeah, just to kind of introduce myself. So I'm a hydrologist. I'm probably more from the numerical side. So my bread and butter really is in developing hydrological and groundwater models. And the motivation for most of my work is really about getting a better understanding of water resource vulnerabilities and also vulnerabilities to hazards like floods and droughts. And I guess this kind of got me interested in working in mountainous areas where you have these really interesting interactions between the sort of more traditional terrestrial hydrology and then components of the cryosphere as well, especially snow and ice. So for the last sort of 10 years or so, I've spent some of my time working across those kind of hydrology and cryosphere fields. And I'll admit it's in part sort of motivated by the tendency of the general scientific community really, in putting a lot of emphasis on the importance of glaciers as water suppliers. And then coupled with that, my slight skepticism of that, given all of the other interesting hydrology that's probably going on in these glacialized catchments. And of course, groundwater is one of those potentially really important components. So I'm actually going to start with a bit of an apology, because if anyone was, I don't think there's any risk of this, but if anyone was tuning into a talk that I gave yesterday at a different World Water Day event, then this is going to be quite similar to the second half of that. So yeah, apologies if there is anyone here that did tune into that, but I don't think there's going to be any risk of that. So okay, so I wanted to start by putting glaciers into perspective a little bit. So the 56 largest glacialized basins in the world, only 5 of them have a glacialized area greater than 10%, and the majority of them have a glacialized area much smaller than that. Now, that's not to say that glaciers aren't an important water resource, but I guess it's a good way of demonstrating that there's potentially a lot happening downstream in these basins that probably affects their role in providing water security to downstream users. And this was kind of the focus of an opinion piece that we published a couple of years ago. The title of that was Looking Beyond Glaciers to Understand Mountain Water Security. And within that, we emphasized the need to sort of rethink the way in which we define mountain water security. And this really was in response to the kind of significance placed on bulk meltwater estimates from kind of glacier models and glacier observation data, which don't necessarily consider the spatiotemporal propagation of meltwater through the terrestrial water cycle. So yeah, water could be stored in wetlands, it could be evapotranspired, it could be in moraines, as we saw earlier, it could be in proglacial aquifers. And those subsurface pathways are the ones that I think are especially interesting. And there's a slightly more recent perspective or opinion piece that's come out. This was a group of hydrogeologists who kind of emphasized the need to really understand this glacier groundwater connectivity. And they highlighted 2 main knowledge gaps, which I'm broadly in agreement with. Firstly, the fractions of meltwater that contribute to groundwater recharge, and we've heard that already. I would also say vice versa. So the amount of groundwater that contributes to proglacial flow is also really interesting. And then, of course, the way in which it kind of propagates downstream and how it interacts. So initially I thought my focus of my case study was probably going to be in the Peruvian Andes, and I'm going to do that, but I hope you don't mind. I'm also going to take us back to Iceland because I've done a bit of work in Iceland as well, and I think it's really relevant, and hopefully it'll add a little bit to what to the work that Sophie's already demonstrated. So I'm going to kick off with the Peruvian Andes. And this is some work that's actually, it's kind of my work. It's actually my PhD students, let's be honest. I haven't done much of it, but I'm gonna claim a little bit of ownership because I am their supervisor. But it's my PhD student, Tom Gribben, who's really led this piece of work. And this is from his first publication from his PhD. And he's been working on these high mountain wetlands, which are locally known as bofedales. And these you can find pretty much all over the Peruvian Andes. They're high altitude wetlands, and you can see one in this picture here. They're actually normally filled with, they're kind of bustling with water. So you'd quite often in the wet season, you'd find lots and lots of water between these little channels. But this is taken in the dry season, so you can see it sort of dried up a little bit. So these bofedales, they cover, it's thought, about 10,000 kilometers squared in Peru alone. And just as a comparison, glaciers cover probably an order of magnitude smaller coverage than these bofedales. They're typically found in mountain valleys, and they're often found in sort of dam valleys, like moraine dam valleys, for example, which can give rise to the formation of these things. They're really important locally for farming, so they're used as grazing land for alpaca, but they're potentially also extremely important for that kind of water regulation and water supply further downstream to the kind of main population centers in Peru. So we're going to focus on a catchment in southern Peru. It's actually in what's known as the Cusco region of Peru. And we're on a mountain range called the Cordillera Vilcanota. And we're focusing on a small subcatchment of within this mountain range, which we just call the Siaprina-Kiscapina catchment, because those are two of the main glaciers that supply meltwater to this catchment. But you can see the glacier coverage probably a little bit easier on here by all the white stuff. And there's also significant bofedale coverage within this catchment, which is shown by the orangey stuff, and also some of the pink bits, which you can't really see in here very well. So the bofedales themselves are generally composed of an organic matter layer, approximately 1 to 2 meters thick. They can be thinner than that, but they're underlain generally by increasingly clay-rich deposits, which form a kind of relatively impermeable barrier that allows water to pond in those regions. We're close to the equator here, so the air temperature range seasonally isn't really very much. You've got a sort of average range between -4 and +8, but it tends to be hovering around freezing, plus or minus 10 degrees. The elevation range, we're pretty high up, so we're getting up to kind of 5,000 meters plus. Now there is a very distinct seasonality in the rainfall, so you have this distinct dry season and distinct wet season in our summer and winter, respectively. So what do we want to do? We wanted to quantify the contribution of water transiting these bofedales to dry season stream flow. And then kind of linked to that, we also were thinking about the way in which meltwater propagates through the catchment. So is the water coming from the glaciers? Is it just flushing straight through? Or is it being absorbed by these wetlands and kind of gradually released? So how do we do this? Well, Tom collected lots of meteorological data, river stage data, snow cover data, but the main component of his work really was a large environmental isotope study. So he was collecting water samples and analyzing them for stable isotopes. So he's actually collected data over a couple of years, but this particular project just focused on 1 year of data from the wet and dry season of 2022. And we've got samples from precipitation, taken samples longitudinally down the river, samples at the glacier outlets on the ice, peripheral groundwater springs that are sort of kind of on the periphery of the bofedales, thought to be indicative of sort of deeper groundwater stored within the talus and potentially deeper sort of glacial fluvial aquifers. And then also water from the wetlands themselves, so taking them from pools and also augering into the wetland and extracting water samples from those augers. So yeah, Tom's really put together a really nice data set of water sample data. And this is just kind of summary looking at oxygenating versus deuterium from the stable isotope analysis. And you see a really nice sort of glacial melt characterization, and similarly for groundwater as well, relatively distinct. Precipitation kind of spans the whole range. It's very seasonally variable in terms of its isotopic composition. But the wetland samples were really interesting. They show a really distinct evaporative signal. And if you've worked with stable isotopes, you know that generally when samples are falling off of the local meteoric water line, so this line here, something is going on. And this is essentially due to evaporation. So lots of evaporation happening within these wetlands. And that evaporative signal actually showed to be a really powerful means to kind of distinguish between water transiting the wetlands and water just kind of passing straight through the catchment. And we can quantify that evaporative signal, if you like, using a metric called the line condition excess, which is basically a quantification of how far these samples move away from the local meteoric water line. And then Tom showed that if you analyze the LC excess and how it changes downstream, there's a clear, it's clearly becoming more negative as you go downstream. And you can see that probably more easily in this plot down here, which shows you how this LC excess, line condition excess, changes as you go downstream. And this is a really strong indicator that river flow is looking increasingly more like wetlandy type water. So then what Tom did is he used the line condition excess as a means to conduct an end-member mixing analysis. So he used this evaporative signal as a means to actually quantify the contribution of water transiting the wetlands to the river. And it's a really robust approach he used. He did lots of sort of corrections for in-channel evaporation, loads of QAing, like removing sort of snowmelt events that might skew the results. Did a load of uncertainty analysis as well, particularly around the end-member selection. And having done that, he determined that between May and June in 2022, which is pretty much the middle of the dry season, or sort of beginning to middle of dry season, water transiting the wetlands contributed up to about 20% of the stream flow. So you're getting about a fifth of the water has certainly gone through the wetlands, which is, yeah, pretty significant amount. Now, it's not conclusive where the wetland water comes from, so we don't know at the moment whether it is glacial melt necessarily that's going in there. It's probably a mishmash of lots of different things. And there's also some uncertainty as to where the other stuff is coming from. So some of it certainly could come from deeper groundwater, so not just sort of shallow groundwater within these wetlands. We have done some geophysical surveys that show pretty definitive evidence for a significant glacial fluvial aquifer beneath the Beaufort itself. And I know that others, including Jeff, I think on the panel, have looked into the sort of significance of those interactions in more detail. But this is very much work in progress. So Tom's now working on developing an isotope-enabled glacier hydrology model to sort of test different hypotheses of these flow pathways, including things like deeper groundwater flows and interactions between glacier melt and the Beaufort. So yeah, watch this space. Things will be coming out in due course. Okay, I'm going to take us back to Iceland. Sorry for doing this, but I think it's useful to have a look at Iceland as well. So this is the study site of my PhD. And here we're looking at, as Sophie kind of pointed out, a big sort of glacier fluvial outwash floodplain. We tend to call these things sanders. And this sander is made up of sands, gravels, really high permeability, high porosity materials. The typical kind of material you might find in typical kind of basin fill aquifer. It gets up to, I think, about 300 meters thick in this location. And I should say, sorry, for some context, we've gone a little bit west of where Sophie was looking. So we're around the other side of Vatnajökull here. It's got quite a distinct seasonality and runoff, so driven by the melt season. And diffuse recharge, so recharge from rainfall into the sander, is thought to pretty much follow the inverse of that. And this, a bit like Sophie's catchment, this is quite a nice, well-monitored catchment. We've got continuous groundwater level data, for example. We've also got runoff, continuous river flow measurements and on-ice ablation and all this kind of stuff. So the question here was really about that sort of interaction component. So do fluctuations in meltwater runoff impact the proglacial aquifer? So is there significant connectivity between the meltwater runoff and the aquifer? And then there was also a sort of climate change aspect in here, and looking at glacier retreats as well. So this is very much a modeling study, and it kind of built on a load of other modeling that I'd done previously. So it's got sort of climate change projections, and it's got a glacier hydrology model. And then essentially what we did is we bolted on a mod flow model onto the end of it, so a groundwater model onto the end of it, to represent that sander. So it includes all of the upstream melt and everything that then ends up as a boundary condition to the model. And essentially what we did, because we ran the model not only over kind of historical periods to test it and validate it and things, we also ran it over the future period because we wanted to look at sort of climate change impacts. Now we ended up with a huge ensemble of different scenarios we could have used. So we just sort of boiled it down to 5 different scenarios that broadly took into account the various different climate and glacier changes that we might see. So what did we see? Well, the model suggested that river recharge was probably not surprisingly highest during the melt season. So you can see this is river basin runoff. So upstream runoff coming onto the sander, and this is the recharge. So it kind of follows the seasonality of the recharge. We found that it contributed up to 39% of the recharge into the sander. So that's including rainfall recharge plus this, so up to about 39% of it. But on average, about 15% of the recharge onto the section of sander we were looking at least was coming from meltwater. So again, a significant contributor. The higher runoff did not necessarily lead to more recharge. So there wasn't a sort of direct correlation between that. And we can see that if we look at these different colored lines, these are those 5 different scenarios, and they don't necessarily sort of map onto each other. Actually, the main control of connectivity between the glacier meltwater and the groundwater is the regional sort of groundwater level, right? So if the groundwater level is lower, the length of the river that then becomes bigger, and you get more recharge seeping into the sander. And that groundwater level, of course, is controlled primarily by rainfall. So you've got a kind of climate driver on here, which is controlling the degree of connectivity between the glacier and the aquifer. But we also, one of our scenarios showed this really interesting behavior. So this plot shows the change in river recharge, so the amount of water infiltrating from the river into the aquifer. And this is the change in the future with respect to the past. If you remember, there was a sort of climate change aspect to this. So we looked to see how do things change in the future relative to the past. And there was a big drop in river recharge for one of those scenarios. And we couldn't really figure out why it was, because the groundwater level, it didn't, we weren't seeing a big rise in groundwater level, for example. There wasn't a significant change in the length of losing river. So why was it? Well, it actually turned out that one of the key drivers of this big drop was because it's benchmark, if you like. So the way this particular scenario was behaving historically was it had a much higher diurnal variability in river runoff coming from the glacier. There's a lot more melt being kicked off by the glacier under this scenario, and a much higher diurnal variability in the river stage. And it was the loss of this diurnal variability that was resulting in this significant drop in river recharge. So this is kind of an indication of a way in which the presence of the glacier itself can be a driver of connectivity. It can enhance recharge, and it's to do with this almost like pumping behavior where the stage is going up and down within a given day, and it's those periodic rises in stage that drive the recharging. So it's just some sort of summary of thoughts. So based on these case studies at the headwater scale, we can say that groundwater can provide a significant contribution to total runoff. glacier melt can provide a significant contribution to groundwater recharge, and the presence of glaciers themselves can enhance recharge to mountain aquifers. Yeah, probably the contributions from and interactions with groundwater and glacialized basins, they will almost certainly perturb the timing of magnitude of water provision to downstream dependence, but we haven't done anything on that scale yet. But there's without doubt a big gap in in what people are doing at the moment, which is we really need to better integrate these glacier melt and mountain hydrogeology into our modeling tools. But I feel like I'm preaching to the converted here because I'm sure you would all agree with that anyway. I think that's my 20 minutes. So thank you very much for listening.
Thank you, John. We just have one question in the chat. It says, from Alan Edmonds, it says, with respect to the study of Boffadales, I notice you have 2 sampling dates of the Boffadale water, and both seem to show alignment on different evaporative trend lines. I was wondering if that has informed the study of the source waters of the Boffadales, including glacial and potentially deeper groundwater.
Good question. So the answer is no, not really, because it gets a bit hazy. So yeah, so you can plot, you can follow this back onto the local meteorite waterline, and the problem is that you have quite a bit of variability in the isotopic composition of the rainfall data, and there I kind of showed 2 sort of extremes from one to the other, but it varies quite a lot, and that sort of it makes the whole thing hazy, because if it's rainfall, yeah, I guess the short answer is yeah, we can't really do that, unfortunately, not at the moment.
Okay, thank you. And we also had a question from Sumitra as well. Sumitra, do you want to ask your question?
Yeah, in the glaciated area, if the aquifer performance test has been carried out, so at different level, if the temperature of the water is varying or not, because in the subsurface water normally has a higher temperature than the surface water. But if the temperature at a greater depth, if it is much lower in comparison to the surface water temperature, then there may be a link of the glacial fed aquifer, if it is done.
Yes, good question. So and is that specifically related to the Peruvian case study or the?
Okay.
Okay, so I'll vouch for both. With the Peruvian case study, no, we haven't. So although we have established some quite shallow wells in the Bofadal, we haven't been able to drill boreholes deep beneath or through the Bofadal into what we think is a glacier fluvial aquifer underneath. And the reason for that is purely logistical. It's a really remote field location. It's very difficult to get that kind of infrastructure up there. And there's probably also a lot of well, it's beyond logistical. There's lots of sort of local considerations to take into account. For example, the people that live there. So in the Bofadal, no. In the Iceland example, yes. Although I have to admit, I haven't looked at those data very much. But there are temperature measurements in the river, and there are temperature measurements for the groundwater as well.
Okay.
And that would be a really useful thing to look at. So thanks for the idea. I'll take that one. I'll take that one back.
So in the field when we work, we explore so many things that we want to share. That's all.
Okay, so we've got one more question about the Bofadal. Have you seen the excess of deuterium for an isotope signature for glacial water input?
An excess of deuterium? No. This is where I would want to call my PhD student in Tom, but I think the answer to that is no. We haven't seen an excess of deuterium in the glacial melt input. I'd be interested to know what the context of the question is.
Felipe, to ask a little bit more for some more information. If you want to contribute some more, Felipe, please let us know. Otherwise, we'll move on.
So while waiting for Felipe to, if he writes a question in, so I noticed that glacier melt had a much heavier isotopic composition than snowpack. And in North America, we see typically opposite the snowpack. So do you know why the ice has a much heavier isotopic composition than snowpack?
I don't. So I know that the isotopic composition of snowfall is really, really variable. And you have some really complicated kind of meteorological, sort of regional meteorological patterns going on there that probably bring about some, I guess, less than normal isotopic composition of snowfall. So I would imagine it's something to do with that. But yeah, no, to answer the question, no, I don't really know why that is.
Okay, thank you. And I guess, I don't see any question. Oh, yeah. Okay. So, Olivia, do you want to read it out?
Sure, yeah. It's to get, this is a continuation of the question from Felipe. It's to get some more data about the origin of the waters, since on some studies there is a signature of glacier water distinct from precipitation, snowpack, springs, and surface waters.
Yeah, no, I totally get the idea. I think again the problem is, and this might be to do with the duration of the field campaign, which I mean there we were just looking at 1 year's data, right? So potentially, I guess you could see over longer term, maybe there is a more distinct signal kind of coming out. Yeah, unfortunately, we didn't feel confident in distinguishing the glacial melt purely on the isotopic composition because of that. The really funky sort of, well, it's rainfall and then it's snow melt as well. And this is the problem with the snow melt input is that you tend to have these quite sporadic snowfall events that then melt out quite quickly. So you don't get like significant snow coverage for a long period. A lot of the time it's falling and then melting pretty quickly. And the isotopic composition of each of those individual snow melts will be different. So it all becomes a bit hazy, and that's why Tom had to put a lot of effort into trying to remove any of that noise to try and pull out the signal really. So that did make it a bit more tricky.
Okay, well, thank you, John, and all the questions. So we now move to a panel discussion moderated by the Secretary General of the International Association of Hydrogeologists, Jane Dottridge. Jane, please take it away.
Thank you, Masaki. I'm pleased that we have an illustrious panel of Professor Soumitra Mukherjee from Jawaharlal University in India.
Good evening. Good evening from India. Good evening.
Professor Geoffrey Mackenzie from McGill University in Canada, and Colin Mayer, Assistant Professor at Dartmouth College in the USA. Starting with Soumitra, what is the role of rivers and fluvial processes in linking glaciers and groundwater? We've already heard some of the comments on this, but please share your insights.
Yeah, sure. You see that I'm working in this field from 1985 till 2024. And the thing is that in the basically in the Indian context, I have worked maximum in the Himalayan area. So the Himalayan area, there are two different problems are there. One is it is seismotectonically active. And second is due to climate change, the precipitation also varying for last several decades. So I remember in 1985 to 1989, when we have done this groundwater exploration in different parts of the Sikkim Himalayas, that is eastern part of the Himalaya. And there we have done extensive groundwater exploration, although some of the groundwater wells, they became inclined so we could not do the pumping test. But in some of the wells where we have done the pumping test, we found out that at say 50 to 55 meters below ground level, where the overturned rock sequence, see, normally the rocks there should be the older rock should be phyllite and younger rock should be Gondwana sandstone. But in that case, the older rock was Gondwana sandstone and younger rock was phyllite. And when we have done the aquifer performance test in that area, we found out that the groundwater which was coming after that pumping well, the temperature of that groundwater was much colder in comparison to the surface water. There is a Tista River, the surface water temperature also have collected. So we have concluded that there must be a glacial fed aquifer. So later when we start working on this Gangotri and Gomukh area, which is the origin of the Ganga River, River Ganges, where we have identified that at the upper reaches, the changes are not much. But when we come to the lower reaches, then we found out that there are lots of changes because of that glacier retreat. The glaciers has retreated in the Himalayan area and its impact has been observed in the downstream. In some of the river where we recently worked, one is the Hindon River. So we found out that its river basin where the rainfall is very high. It ranges in between 650 millimeter to 700 millimeter per year. But after the spell, the whole catchment area was full of water. But immediately within 3-4 days, the water vanishes. And then another river, which is in that Alaknanda and other river channels, we found out that there are some U-shaped valleys, which are not V-shaped valleys. In the U-shaped valleys, which is one of the significance of that past glacial valleys, and the rocks, which is at the bottom of the river basin, we found out that there are some striation marks, which signifies that these may be glacial striations. So our work is continuing in this area, and unless we complete the detailed study of fluvial geomorphology, glaciology, and aquifer, so we cannot say in a concrete evidence that what is the flow path of the glacial melt, surface water, and to the groundwater, because in all the places it is the glaciers are not feeding the groundwater, but in most of the places the fluvial melt, they are feeding the groundwater. But due to the tectonic activities, the fractures are sometimes opening and sometimes closing. So our work is yet to be completed. We are doing this work, and we need a lot of collaboration from IAH experts, as well as through this forum, I invite for the collaboration in this area. So in India, we are working in this Ministry of Water Resources, there is Namami Gange program, where we are working extensively on this river Ganges as well as other rivers. And our concern is not only the glacier, surface water, as well as groundwater linkage, but our concern is to infer the possible disaster in the due to that glacial melting. And what we have understood that there is a glacial niche in Himalayan area. In all the places, the glacial melting is not the uniform. In some part of the western part of the Himalaya, the glacial melting is slow in comparison to the eastern part. So we have studied with a very advanced instrument, that is SEVAN detector, Space Environment Viewing and Analysis Network, which was funded by NASA. And we have studied the Sun Observatory, Heliospheric Observatory data, and we have inferred that besides our anthropogenic activities, there are lots of activities which are taking place due to the changes within the sun, as well as the cosmic ray variability. So our work has already been published in different journals, and we will be happy to share our work, and we are looking for future collaboration with you. Thank you. Thank you very much.
Thank you. I'll pass on to Jeff with a related question. What are the potential roles of groundwater in sustaining flow in mountain rivers while glaciers are retreating?
Hey, thank you, Jane, for the
the question, and also thanks for this panel. It was a really interesting discussion, and thanks to UN Water and UNESCO and IAH for organizing this. Yes, the mountain regions, as a bit of background to get to the question of groundwater, are really critical for the world's water supply, right? Daniel Vivarelli, did some work showing that about a quarter of the world's population rely on mountain regions for their water supplies. And so I'd argue that in mountain regions, much of our focus as a broader natural sciences community and water resource management managers have really been on glaciers and seasonal snowpacks. And these are obviously critical components of the water budget, particularly during the dry season or summer when downstream water resources are really stressed. But this meltwater from glaciers in particular is under threat. We know that almost ubiquitously, mountain glaciers are rapidly retreating, leading to less meltwater and providing less water for critical river flows. A recent NASA study sort of suggested that with a 1.5-degree warming by the end of the century, about half of the world's glaciers, mountain glaciers, are expected to disappear. So within this context, and maybe preaching to the choir, but groundwater is critical, right? Groundwater, well and visible, can really buffer these changes. So groundwater is recharged, and with sort of summarizing a little bit we've heard from multiple people today, groundwater is recharged by snowmelt, rainfall events, and even glacial meltwater in mountain environments. Groundwater storage in alpine environments includes things like talus slopes, work that Masaki's done, fractured bedrock, porous sediments that can act as natural reservoirs for groundwater, and also can be stored in alpine wetlands. In South America, we talk a lot about bofedales or paramo systems, and Jonathan gave a really great introduction to that for their site in southern Peru. So these storage systems are really critical. They allow water to be recharged, stored in the subsurface. This water slowly moves through the subsurface and is eventually released either directly into rivers and streams as base flow or via springs to the land surface that eventually will join up into our larger hydrologic system. So as an example from my own work, we've been studying the role of groundwater in sustaining mountain rivers and streams in the Cordillera Blanca. This is more in northern Peru, whereas Jonathan's work was a bit farther to the south. We've been studying here for the past 20 years, and this iconic mountain range, the Cordillera Blanca, has the highest density of glaciers in the tropics. So this mountain range provides really critical water for the arid west coast of Peru. The west coast of Peru is a desert, but it's also been a growing agro-industrial hub with large-scale international exports of agricultural produce for the rest of the world. So just as an example, in 2022, Peru exported more than $22 billion worth of agricultural goods globally. And about 20% of this water is through two massive irrigation projects called Chavimochic and Chinekis, which rely on water from the Cordillera Blanca. So just to give you a sense of this role of mountain water and mountain groundwater really has a much broader impact. So we've used a variety of research methods to understand just how much groundwater is actually leaving these mountain systems. So we found that in many of the glaciated valleys in the Cordillera Blanca, in some cases, it can be up to half of the dry season flows are actually from groundwater as opposed to from glacial meltwater. And that this water that we see, this groundwater that's making into rivers and streams, usually has sort of an age and been recharged and spent anywhere from 6 months to a couple of years on average in the subsurface. So there's a bit of a retention and storage and slowing down of the hydrologic system, and the water can then subsequently be released into the hydrologic system for downstream flows. And as we go all the way down to the coast, we think that it could be up to, in some instances, up to 75% of the flows of water that actually make it for this irrigation system could be from groundwater as opposed to glacial meltwater during the dry season, just really indicating the importance of groundwater in these systems. And again, these are iconic systems, glaciers everywhere, but at the end of the day, at the larger scales, really groundwater is really what buffers these systems and keeps them going. So moving forward, I'd argue that we really need to include groundwater as part of our mountain water resource investigations. I mean, again, the panelists, I'm preaching to the choir, but groundwater is just this key component to this. And then obviously this is the year of glacier protection, as we've been hearing about, and glaciers are critical for mountain water resources. But as we look forward to decreasing glacial meltwater contributions in the future, it's really important that we expand our views to include the invisible and to include groundwater. So thank you very much, Jane.
Thank you, Jeff. Now passing to Colin as the representative from the Early Careers Network. looking to the future, how do you foresee the impacts of climate change on the interaction between glaciers and groundwater?
Well, hello everyone. Thanks, Jane, and thanks to all the panelists. It's great to be here. I'm a glaciologist, so I study the glacier side of this system. And I want to make 3 points today about the way that glaciers are interacting with the groundwater in a changing climate. And the first one is to talk about how the subglacial hydrologic system works. This was brought up a little bit in Sophie's talk earlier. The next point is how that subglacial hydrologic system is going to change with changing climate. And then the last point is to talk about open opportunities for how glaciers and groundwater are interacting. And that is coming from a different perspective than what we've heard today so far, which has been focused on how glaciers are really impacting the groundwater system. And I'd like to talk about the reverse just for a moment. So the subglacial hydrologic system is this very interesting and delicate balance that happens at the base of a glacier. So we have a glacier, a mass of ice sitting on top of some sediments that are full of water, and we've been hearing a lot about how that meltwater from the glacier can recharge those sediments and then recharge the proglacial sediments. But right at the interface where the glacier sits, on top of those sediments, there's some water that flows along there, and that water plays a really important role in lubricating or controlling the interface. And that interface, the sliding that happens at that interface causes the glacier to accelerate or even slow down in certain contexts. And so having knowledge about what water is flowing, how it is distributed, how much water there is, and what that water pressure is, or the hydraulic head of that water, is crucial for us to understand the glacier dynamics and to be able to project those glacier dynamics into the future. And so we can think of sort of two end member situations. If we have lots of water and it's collected into sort of river-like networks, that we would see in the subaerial environment, that sort of channelized dynamic is very interesting in the subglacial system because it sort of can dry out parts of the bed and reduce this lubrication effect. And so in contexts where you get large subglacial streams, we would think of those as systems that actually have a feedback where as you add meltwater to the subglacial system, the glacier can actually slow down. And this is the opposite dynamic to what we hear about when we hear about meltwater getting to the base of glaciers and causing them to accelerate. And so that's what happens when the water at the base of the glaciers, isn't able to channelize and it sits in very sort of distributed pockets. And so the dynamics, whether you have this distributed pockets or this riverine system, that comes down to modeling and sort of trying to observe this subglacial hydrology system. And so if it is distributed, you add a little bit of meltwater, then that's when you can get this sort of strong lubrication effect. So we can talk about now that the second point is, how is this subglacial hydrologic system going to change with a changing climate? Well, what we have learned about the subglacial hydrologic system is it really depends on the time scale over which meltwater is being added. If we're getting short bursts of meltwater, then those short bursts can make it into something like a distributed system, and then they can cause little bits of acceleration. If there is sustained long-term melting, then the water can sort of coalesce into these channels and actually start to strengthen the bed and actually start to slow down the glacier. So the timing for how the meltwater gets to the bed is crucial for how the subglacial hydrologic system is going to respond in a changing climate. Okay, now with that base of knowledge, we can tie it back to groundwater. The groundwater system, there's these huge aquifers underneath the glaciers, as we've been talking about, and we know that the subglacial hydrologic system plays a strong role in influencing these groundwater aquifers. There's a great deep borehole drilled in next to the Greenland ice sheet, showing that as time has progressed, there's actually been a loss in hydraulic head in these groundwater systems due to changes in the subglacial hydrologic system. So that's a lot of what we've been hearing about today. But there's also the reverse, which is, how does the groundwater system influence the subglacial hydrologic system? And as the water, changes because of seasonal inputs or changes because of, as the climate changes and we start seeing different orientations and distributions of subglacial hydrology, we're going to expect a larger input where we actually have water coming out of the hydrologic system, the groundwater system, and into the subglacial hydrology system. And we saw a few discussions of that in the earlier talks. And so this really represents an opportunity for glaciologists and groundwater hydrologists to collaborate to understand, okay, we want to tell you how much water is being input into the aquifers for recharge, but the glaciologists also want to know how much of that water can be brought into the subglacial hydrologic system. So with that, just the 3 points I made were about the subglacial hydrology, how it works, where water distributed, how that might change in the future, and some of these opportunities for collaboration. So thank you.
Thank you very much. That was some interesting points from everybody. I don't know whether there's any, don't see any questions in the chat for the panelists, so I'll hand back to Masaki.
Well, thank you, Jen, and thank you to the three panelists for making interesting points from different angles. So now we will end this webinar with closing remarks by James Thornton from Mountain Research Initiative, representing the Groundwater Youth Network and Early Career Hydrogeologists Network. James, please.
Yeah, thank you very much indeed, Masaki, and hello to everybody. So how to summarize and maybe add something to what's been said already in these very detailed and excellent presentations. It's a difficult task, but I'll try nevertheless. I think the first thing to mention or to underline really is the inherent complexity of these systems, the number and diversity of different processes which are operating and interacting with one another in a given catchment or a given region, all of which, of course, demonstrate a lot of variability or heterogeneity in space and time. And so this really, as many of the talks have already demonstrated, requires us to work in a very interdisciplinary fashion and bring expertise from different perspectives and different disciplines. The second point, I think, is really just how fundamentally important monitoring of the type we've heard about today really is. There are several of these very well monitored catchments now around the world, which have really, as we've heard, revolutionized our understanding of groundwater in mountain environments and increasingly also interactions between cryosphere and groundwater. But of course, such monitoring is really challenging and very expensive. These are remote regions. The subsurface is, of course, inaccessible, generally speaking. And certainly there's this growing gap between the amount of data we can obtain pertaining to the surface, especially from satellite remote sensing, and the subsurface, which is obviously much more challenging. And so this is, I suppose, a plea also to funders that this fundamental monitoring and holistic monitoring really needs continued support if we're to continue to expand our knowledge of these complex processes. And there are several specific ways in which we can go about this. So, for example, the development of three-dimensional geological models to really constrain the patterns and characteristics of the subsurface, the use of various geophysical approaches, including some which are emerging, like terrestrial gravimetry, and of course using a suite of complementary tracers. We've heard isotopes today, but of course there are other tracer approaches which are very complementary and in some cases enable us to learn more about for example, the source components of stream flow, the residence time of groundwater, and also how surface and subsurface waters are exchanging. We also need to remember that even parts of the water balance which we may think we can constrain very well, and we can in normal circumstances, are also more tricky in mountains. For example, simply constraining precipitation in very snowy and windy environments can be really difficult and can lead to large uncertainties, up to maybe 100% in some cases. So this is normally the input to our water balance, a known term in our water balance equations and input to our models. So this is really on the monitoring side and understanding the processes. But next, really to inform policy and resource management, we need to develop some strategies, and we've maybe heard a bit less about this today, to actually transfer the knowledge which we've gained in these very often small but well-monitored study catchments across the world's mountains and the upstream and downstream connected areas much more generally. And this is both this spatial extrapolation to understand, for example, the present day hydrological system and dynamics, but also then, of course, for making future predictions or projections on a range of temporal scales for a range of end users. But I mean, this is, I think, a bit the holy grail, really. What environmental managers and policymakers need is some kind of insight into the future as well. And this is, of course, where modeling comes in. And I think certainly there's some scope to build on, I suppose, the existing modeling efforts and maybe develop systems or coupled models which are more comprehensive, which deal with this entire system in a single tightly coupled fashion, including the glacier and snow dynamics, the surface and subsurface flows, evapotranspiration, and the exchanges between these different parts of the water cycle. Traditionally, glacier hydrological models have only included relatively simplistic representations of the groundwater processes and components. And vice versa. Groundwater models traditionally have required this estimate of recharge as an input, meaning all the work to derive snow melt and glacier melt and how this percolates through the unsaturated zone has to be done separately. And in some cases, if you just stick these types of models together, you also get some strange issues at the edge cases where maybe not everything matches up perfectly, so to speak. So I think there's really a lot of potential for these more sophisticated coupled models where these processes and their interactions are represented explicitly in time and space according to physics principles. And then this also enables one to integrate really a wide variety of data to calibrate and evaluate them, because really they're simulating the majority of states and fluxes in time and space. And maybe just to take this perhaps a step further, given, of course, such models can often be very computationally intensive, I think we need to also, as a community, try to consider exploiting the possibilities of artificial intelligence a bit more, in particular deep learning, to maybe replicate, if you like, the predictions of these more physics-based models, and therefore be able to generate very high resolution predictions of these entire systems, again in a spatially and temporally explicit fashion, really much more widely, both for the past or present, but also for the future. And so this, I think, is going a bit towards this vision of a digital twin or a model of everywhere, Keith Bevan's models of everywhere philosophy, where really one can integrate the physics models with this these more data-driven approaches and make the most and exploit the data which we have, which is, of course, both the in situ observations, time series, and other types of data, as well as more spatially explicit map data, if you like, from satellite remote sensing and drones. And in this way, I think we can really respond to the crucial need of policymakers and decision makers to try to really understand how groundwater will change. Will it buffer the change in stream flow expected due to changing cryosphere alone, or will actually, as some studies have already started to show, will declining groundwater actually exacerbate the reductions in stream flow which are associated with this direct effect of changing cryosphere. So this is, of course, a kind of a positive feedback mechanism, if you like. And if you don't include groundwater in your model, then you may be missing this part of the story, and you may be overly optimistic. But I think by bringing together the expertise of the different communities and doing this monitoring and modeling together, I think there's lots of potential to also improve our knowledge of these complexities, and therefore provide more informative data to decision makers and to society as a whole, even though, of course, most of these glaciers cannot, unfortunately, be saved. Thank you very much, Masaki. Back to you.
Well, thank you, James, for summarizing the current knowledge and then making suggestions for future research. So this concludes our webinar. Thank you, everyone, including the presenters and panelists and audience, for attending the event. And happy World Water Day.
Super.
Thank you.
Thank you very much.
Thank you.
Thank you, all of you.
Thank you. Thank you very much.
Thank you. Yes.
Thank you. for your very good presentation.